morning. I'm Edoardo Mascalchi. I work for CLEPA, the European Association of Automotive Suppliers, where I work in the R&I department as project manager. And today, with Joost van Doorn from NXP, we will present you the multi-brand specification and communication protocol in the ENSEMBLE project. In this presentation, we will first give you an introduction of how the work has been structured in the project and then how the multi-brand specification has been defined. Then, my colleague Joost will give you a focus on the communication protocol. So let's see how the work has been structured. The function has been defined in Work Package 2, and as you may see, Work Package 2 is linked to other three work packages. Work Package 3, where the platooning functionality has been implemented, Work Package 4, where the platooning has been assessed, and the Work Package 5, where the tests and the demonstration have been designed. But not only, we also take input from these work packages in order to ensure a very good functionality. Furthermore, within Work Package 2, the iterative process has been designed. And in this way, we allowed us to have a very safe functionality, always keeping safety experts in the loop. Let's see how we designed the multi-brand specifications. We have two levels defined in ENSEMBLE. The first one, the platooning support function, the one that we are demonstrating today and that has been implemented. Here, the driver is fully responsible. In the second level, the one that moves towards automation, the platooning autonomous function, we are just giving specification and requirements, and in this case, the drivers in the following trucks are not responsible, are out of the loop, and so we can also go closer with the time gaps. What is common to both levels? The platooning layers. These are the basis concept of ENSEMBLE that ensure multi-brand platooning. Let's see how. We have the basis, the bottom part, that is the operational layer. This is specific to each OEM and is closed for each truck and each brand. What is common to everybody is the tactical layer. This is the common part that ensures trucks of different brands to be able to communicate each other. Above them, we have the strategic layer that organizes the platoon and organizes rendezvous, etc., and the service layer that enables a new set of services dedicated to platooning. Let's deep dive in this platooning support function. We started with ACC. This is exactly as the ISO described that, with limited deceleration, with lane keeping that is optional, follow to stop is mandatory, while start from standstill is again optional. Since everything is compliant with the ISO, the driver is therefore responsible for both the dynamic driving task and respecting traffic rules. What ENSEMBLE added is the V2X communication part. This means safety, because we can get earlier notification of emergency braking thanks to the V2V communication that are faster than an onboard sensor like a radar. But we also have platooning coordination, cohesion control, limited speed differences, better string stability, and finally the possibility to receive information from infrastructure. This obviously leads to more comfort and less stress for the driver, and as a technology we used ITS G5, but clearly the protocol is technology neutral. What you will find in the next presentation is that this is absolutely different from CACC, because we have a dedicated set of messages designed for ENSEMBLE. Let's start with the use cases. Clearly, once we define the platooning levels, we can then start the definition of use cases. And the first set is linked to the engaging to platoon, how to start platooning. We have two different situations when joining from behind, or as a single vehicle, or as a platoon. And we also considered the merge in between as a single vehicle, so a single vehicle that enters in the middle of a platoon. This is the stage where the V2V communication is established, including security features. And once this communication is established, we are in platooning mode. So apart from the steady-state platooning situation, we also investigated different specific situations like follow to stop, emergency braking, gap adaptation, cut-in, cohesion request, and warning for system issue. Finally, we have the disengagement. So specific situations are described depending on the truck that wants to leave. If it is the last one, if it is someone in the middle of the platoon, or if it is the first one. And leaving can be activated with a button, pressing the brake pedal, steering out from the platoon, or for other issues like connection loss. We also consider the split of the platoon, so that situation where we end up with two smaller platoons. For each use case, we then define a set of specification and requirement. And specifications are for the tactical layer, the common part for each truck, and requirements have been given for the others, so longitudinal support and actuators, sensing technologies, V2V, I2V, and HMI. As part of this iterative process within Work Package 2, we ended up in an ASIL B functionality. This means that only few safety requirements are needed to ensure safe platooning with the platooning support function. The next step is the platooning autonomous function. In this case, we move from a support function to a more autonomous functionality, where the first truck is driven by a human, while the following trucks are with the driver out of the loop. This means having the V2X connectivity as an enabler for a follow me functionality. And time gaps are shortened thanks to a braking performance estimation functionality that will be a key feature of this second level. And we will discover that in our next event for ENSEMBLE. But now I will hand over to Joost van Doorn from NXP that will give you the focus on the communication protocol.
So good morning, my name is Joost van Doorn. I am working with NXP Semiconductors as an architect in our Automotive Systems Innovations Lab in Eindhoven. We are involved in the ENSEMBLE project primarily as partner for DAF Trucks to develop their truck and also contributing to development of the protocol itself. But why do we need a protocol? Communications protocol for platooning is a key enabler for the platooning use cases. We need a protocol to discover other trucks in the neighborhood that are capable to platoon at all. And then we need a protocol to join trucks into a platoon and drive stable at a platooning distance. And finally, in case of braking, we do that in an orchestrated manner by using the communication protocol. Platooning takes place in 4 phases. You can see them here. The first phase is the standalone trucks phase. There's no interaction between trucks at all. The second phase is what we call platoon join. That means 2 trucks start to interact with each other to build up a platoon. The third phase is a phase of platooning trucks. And here the trucks are actually communicating to establish a platoon or to keep the platoon alive. And the fourth and last phase is when the truck leaves a platoon or a platoon is split up. Now, what about the communication in these various phases? In the first phase, so the standalone truck phase, each truck is controlled by its driver and there's no interaction from any platooning aspect. The goal in this phase is to find another platoon that you can platoon with. And in order to do so, each truck publishes its platooning capabilities. And we do that by using the ETSI-based CAM messages. There are standard messages defined by ETSI, which is the European Telecommunication Standardization Institute. We extend that standard defined CAM message a bit by adding a platooning container. Through this container, each truck can publish what its platooning capabilities are. So in the standalone truck phase, let's assume that 2 trucks have found each other and they want to establish a kind of relation by creating a platoon or join an existing platoon. The truck that wants to join sends a request. Well, in this case, you see that truck 2 wants to join truck 1. It sends the join request, and here truck 1 decides if he approves the join and sends a response accordingly to truck 1. So it accepts or rejects the join request. For that, we have defined two new messages. We are called platooning management messages, or PMM. So it's the one end, the PMM join request. The other end is the PMM join response. Then we end up in the next phase where indeed the trucks have linked into a platoon. And here the goal is to keep the platoon intact while driving at this platooning distance. And in order to do so, each truck broadcasts control-related information. And this information is used by the neighboring trucks. For that, we've defined a new message type. It's called the platooning control message, and this message contains information on its current position, the configuration, control parameters, and it's also used to share status among trucks. Well, we end up in the last phase of the platoon, where a platoon is either split up or a truck leaves. During this phase, we keep the platoon intact, but we first start to increase until the gap is at a safe distance. And if the gap between the two trucks is at a safe distance, we give the control back to the driver. And while this is the case, the PCM messages continue to be exchanged. The communication protocol all comes with security aspects, and there are two of them. Now, first of all, of course, I want to focus on the goals. What do we want to achieve with protocol security? First of all, we use well-established security mechanisms, which are common. We want to make sure that messages cannot be changed, and we can verify that. We also want to assure that messages are sent by trusted vehicles, and that can also be verified. And third of all, we want to make sure that each message remains a secret, so nobody can eavesdrop into these messages. Which aspects do we use to achieve these goals? Well, first of all, we use message signing, which is quite common within all types of ETSI messages, and it provides message authentication. Message authentication consists of two aspects, meaning the message cannot be changed. So from the moment it left the transmitter until the moment it arrived at the receiver, the message did not change, and the message is coming from a trusted vehicle. The other aspect is about message encryption. Message encryption is actually new in platooning. We have two flavors of message encryption that's being used. The first one is the asymmetric encryption, and we use that when joining a platoon. The second one is the symmetric encryption, and we use that when the platoon is active. The table below shows a difference between the two. Asymmetric encryption is used when there is no shared key. When two random trucks want to platoon, they do not share something secret that they can use to do encryption. So in this case, we use the asymmetric encryption. That's the positive aspect of asymmetric encryption. The downside to this is that it is rather slow. Symmetric encryption, on the other hand, is really fast, and we need that during the platoon phase because we exchange high-frequent control messages. But we need to have a shared key to accommodate symmetric encryption. Now, to dig a bit deeper into these security aspects, we start with signing. Signing is done with all the message types. So here you see both truck 1 and truck 2 are sending CAM, PMM, and PCM messages. Each message comes with a signature. So if you, in this case, assume that truck 1 is sending a message to truck 2, truck 1 creates this signature, and for that it uses its certificate. When receiving this message, truck 2 can verify the signature, and if that verification succeeds, then it knows that the message did not change, but it also knows that the message is coming from truck 1, which also has this ETSI certificate. Both certificates trace back to this common root certificate. So as a result, truck 1 knows it can trust truck 2 and vice versa. Now in the encryption and then the asymmetric flavor first, it is used while joining a platoon. it starts with both truck 1 and truck 2 creating a key pair. Key pair consists of a private key and a public key. The private key is the super secret key that never leaves the truck. Public key is a key that can be used to exchange between trucks. Now, if we assume that truck 2 wants to join truck 1, truck 2 sends a join request message, and inside that message, it puts the truck 2 public key. So upon reception, truck 1 knows the public key of truck 2, and it will create yet another key, which is called the platooning group key. It's the blue key you see here appearing. This blue key is actually the symmetric key that we want to use when platooning is active, where we need the performance, when we exchange high frequent control messages. So, but as you perhaps might remember, that key needs to be present in both trucks. So how do we make sure that the platooning group key ends up in truck 2? For that, truck 1 sends a join response message back to truck 2, and it copies that blue platooning group key into the message. It also copies its own public key into the message. But if truck 1 will send a message like this, everybody can listen into the message and determine the values of these two keys. That's not what we want to do. We want to make sure that the join response message is encrypted. Encryption is done by truck 1. In order to do so, it combines its own super secret private key with the public key of truck 2 it received, and by combining these keys, it can encrypt the message, and the join response message then becomes asymmetrically encrypted. Upon reception by truck 2, a similar process appears, and there truck 2 combines its own super secret private key with the public key it received of truck 1. Through that, it can decrypt the message and determine what the value of the platooning group key is. But in practice, of course, it's not only about encryption, because signing is added on top of that, meaning that both messages are accompanied with a signature that can be verified, so both trucks can convince each other that the message was not changed and it's coming from a trustable partner. So if we have gone through this very complex phase, we end up in the encryption, in the platooning active phase, where the symmetric encryption is being used. And as you can see here, the symmetric encryption is actually quite simple, because now both trucks share that same secret key, the blue platooning group key. So here, exchanging messages and encryption is done by just using the blue key to encrypt the message when sending, and using that same blue key upon reception to decrypt it again. Of course, in practice, here signing is added as well. So with the signature, which can be verified, the receiving trucks can convince themselves that the message was not altered and it's coming from a trustable partner. So in summary, the security through the various platooning phases. In the standalone trucks phase, we only have signing. We want to make sure that the messages are not changed and it's coming from a trustable partner. During the platoon join phase, we use the asymmetric encryption, that complex scenario that I described, to make sure that the platooning group key is distributed in an encrypted message. But on top of that, we also use signing. In the phase of the platooning trucks, we use the fast symmetric encryption with the shared key, and also signing. And on top of that, the blue platooning group key is refreshed every minute using the key update mechanism. And finally, in platoon split and leave, we basically use the same encryption and signing as we use in the platooning trucks phase, and also here the key update mechanism is used. And we now finally move over to our conclusions, and for that I transfer to Edoardo again.
So, what are the conclusions? We made multi-brand platooning possible in ENSEMBLE, and we did that using specification and requirements that we agreed with 7 different OEMs. An iterative process that we made in Work Package 2 ensured safe platooning, and we also investigated a broad set of use cases as well. Furthermore, a dedicated platooning communication protocol has been created, including cybersecurity features, and these will be an interesting input and suggestion for standardization bodies. And finally, the next step is going towards automation thanks to the platooning autonomous function that we will discover in the next event of ENSEMBLE. Thank you.